We are in Chapter 7, Estimating Parameters and Determining Sample Size. Section 7.1 is Estimating a Population Proportion. This section presents methods for using sample proportions to make an inference about the value of a corresponding population proportion. Our point estimate is a single value used to estimate a population parameter. And for our class, we're going to be dealing with p-hat, which is going to estimate our proportions, and x-bar, which is going to be the estimate for our mean. The sample proportion p-hat is the best point estimate of the population proportion p. P-hat is an unbiased estimator of p. The next thing that's big for us is confidence intervals, or interval estimator. This is a range or an interval of values used to estimate the true value of a population parameter. And we have a confidence level, and this is the probability of 1 minus alpha, such as 0.95 or 95%, that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. And alpha is called the degree of confidence or the confidence coefficient. An example of a correct interpretation of a confidence interval is we are 95% confident that the interval from 0.405 to 0.495 actually does contain the true value of the population proportion p. And we use confidence intervals and even confidence levels when discussing things in real life. So a lot of times when you're done taking an exam for a class, you walk out of that classroom and you're saying, I am so much percentage confident, or I'm pretty confident that I passed, or that I received an A, or something along those lines. And so we just need to add some numbers into it this time, and we're making it more of a statistical confidence interval. So the first example that we have here is the USA Today Gallup poll asked 1,006 adults, Americans, how much it would bother them to stay in a room on the 13th floor of a hotel. Interestingly, 13% said it would bother them. The margin of error was 3 percentage points with 95% confidence. Which of the following represents a reasonable interpretation of the survey results? For those not reasonable, explain the flaw. So the first thing that we have is part A, and this one says we are 95% confident that the proportion of adult Americans who would be bothered to stay in a room on the 13th floor is between 0.10 and 0.16. So how did they get the 0.10 and the 0.16? So if you look at this, we have 13% are bothered, and it says with a margin of error of 3 percentage points, and that margin of error means a plus or minus 3 percentage points. And this means that if you did 13 minus 3, you get 10%, and then 13 plus 3, you get 16%. And so this is going to be between 10% and 16%, which is the same as that 0.1 and the 0.16. So this one seems pretty good, but I'm not going to say anything yet about it. I'm going to move on and look at the other three that we have for this problem. So the next one says we are between 92% and 98% confident that 13% of adult Americans would be bothered to stay in a room on the 13th floor. And this one is not correct. And the reason why this one is clearly not correct is because of this. Our confidence interval does not, our confidence level does not change. So that confidence level is 95%, and we don't change our confidence level. So this one is not correct, and the reason why is because the level of confidence does not change. So it's not varying. Part C says in 95% of samples of adult Americans, the proportion who would be bothered to stay in the room on the 13th floor is between 0.10 and 0.16. So this one has that 0.10 and the 0.16, but if you look at the difference between part A and part C, it says in 95% of samples of adult Americans, the proportion who would be bothered to stay in a room on the 13th floor is between 0.10 and 0.16, versus part A, which says we are 95% confident. And so this one is not correct also. And the reason why is because the interval sets the standard for all other intervals. So that's not correct. And so we have this is not correct either. With the reason is this interpretation suggests that, that the interval sets the standard for all other intervals. And then part D says we are 95% confident that 13% of adult Americans would be bothered to stay in a room on the 13th floor. And with this one, it's not correct. And we also don't know anything about the interval, so we don't know between what values. So this one is also not correct. And the reason why is because there's no interval that has been given, or margin of error. So no interval is given about the population. And so since we found the errors in B, C, and D, we know that part A is our correct answer. And so again, to state your conclusions, which is a big part of statistics, is we are 95% confident that the proportion of adult Americans who would be bothered to stay in a room on the 13th floor is between 0.10 and 0.16. At the bottom of the page it says, a confidence level of 95% tells us that the process we are using should, in the long run, result in a confidence interval limits that contain the true population proportion 95% of the time. And again, this is the true population proportion 95% of the time, unlike part C, which is talking about the samples. On the next page, it says, suppose that a random sample of size n is obtained from a population in which each individual either does or does not have a certain characteristic. So our sample proportion is denoted p hat, and we find that by taking x divided by n, where x is the number of individuals in the sample with a specific characteristic, and the sample proportion p hat is a statistic that estimates the population proportion p. So the example right below that says, in a town of 500 households, 220 have a dog. The population proportion of dog owners in this town, expressed as a decimal, is p hat. So for our town here, it would be the total number of people that have a dog, which is 220, divided by 500. It does ask to express it as a decimal. I'm going to go ahead and round just 2 decimal places and say this is 0.44. And note at the bottom it says a second survey of 500 households would likely have a different estimate of the population proportion of households that own a dog. Because the value of p hat varies from sample to sample, it is a random variable and has a probability distribution, which we discussed earlier in this unit. So to get the sense of the shape and center and spread of the sampling distribution p hat, we can obtain a random sample of data sets over and over again, get a list of the sample proportions, create a histogram of the sample proportions to gain an idea of the shape of the distribution, calculate the mean, gives us an idea of the center of the distribution, and calculating the standard deviation will give us an idea of the spread of the distribution. The critical value is the number on the borderline separating the sample statistics that are significantly high or significantly low from those that are not significant. And so remember that you have values that are significantly high, and we have values that are significantly low, and we've seen this now for a while. And in the middle there's going to be the values that are not significant. For example, a 95% level of confidence when alpha equals 0.05 implies that 100 different confidence intervals are constructed, each based on a different sample from the same population. Then we would expect 95 of those intervals to include the parameter, and 5 not to include the parameter. 95% of the time the parameter will be included in the interval. And so on here you can see that when you deal with confidence intervals, that confidence interval is going to go in the middle. And so our level of confidence is going to go in the middle. And the reason why is because of that plus and minus idea that we saw with the margin of error. And so that means that you have to take alpha and divide by 2 in order to put each of those percentages in the tails. So our lower limit and our upper limit. Remember, total area under the curve should add up to 100% or 1 as a decimal. So a 95% level of confidence does not tell us there's 95% probability the parameter lies between the lower and the upper bounds. So we have a table here, and this table, I'll give it a star, are the more widely used confidence levels. And so the more widely used confidence levels are 90%, 95%, and 99%. And so if you were to write those as a decimal, you would have 0.9, 0.95, and 0.99. So alpha here is found by just doing 1 minus our confidence level. And 1 minus our confidence level, we would get 0.10 from 90%, or 0.9. And then 1 minus 0.95 is 0.05, and 1 minus 0.99 is 0.01. To calculate our critical values, we're going to do that right in the example right below this table. But these again are the ones that we are more widely using. And so you're able to not have to calculate these every single time. You can look at your table. However, some of the problems are not going to have a 90% confidence, 95%, or 99% confidence level. So for example, right below this, it says calculate the critical value for a 98% confidence level. It says round 3 decimal places. So since it's a 98% confidence level, I'm going to go ahead and draw my normal curve. Again, since we're dealing with confidence levels, that 98% needs to go in the middle. So anytime, again, you're dealing with confidence levels, you need to have that confidence level placed in the middle. And that means that alpha is equal to 1 minus 0.98, which is 0.02. And then dividing the 0.02 by 2 is how much we're going to put in each of these tails. So 0.01 is going to go in each of these tails. So I need to find the cutoffs here. I'm going to call this one Z1 and this one Z2. Again, remember, we will be dealing with standard normal since we are dealing with Z's. And so that means in the middle here would be 0. So we know that on a standard normal, the mean is 0, standard deviation is 1. And in order to calculate Z1, we need to use inverse norm. And remember, inverse norm is area to the left, so 0.01, the mean, and the standard deviation. And then to calculate Z2, we have to also use inverse norm. But this time, for inverse norm, area to the left of Z2 is going to be 0.98 plus 0.01, or 0.99, the mean and the standard deviation. On your calculator, we are going to go to second, vars, and go down to inverse norm. The area that we are going to type in for our first Z value, Z1, is going to be 0.01. And the mean is 0 and the standard deviation 1, since it's a standard normal curve. Select enter and enter one more time. To get the second t value, we're going to go to second, vars. We're going to go down to inverse norm. The area to the left on this one is going to be 0.99 with the mean of 0 and standard deviation of 1 because it's a standard normal distribution. Our z value for the second one, hitting enter again, we get 2.326, and the first one was negative 2.326. So from your calculator, we arrive at Z1, which is negative 2.326, and Z2, which is going to be 2.326. Remember, our graph, our bell-shaped curve, our normal curve is symmetric about 0, so it should make sense that z1 and z2 are the same value, with one being positive and one being negative. So the critical value that you would use if you look up above at your table would be the positive one. And so this would actually be the value that you would have to use when we get into the later part in this chapter and it asks you guys to use that critical value. The requirements to create a confidence interval for estimating a population proportion P, the 3 requirements are: the sample is a simple random sample, or SRS. 2, the conditions for the binomial distribution are satisfied. Please go back in section 5.2 and look at the 4 things that you need for it to be a binomial distribution to review. And then 3, we need to verify that the normal distribution is suitable approximation to the binomial distribution by verifying both n times p is greater than or equal to 5 and n times q is greater than or equal to 5. So these are the requirements that we would have to check in order to say that we can find a confidence interval for estimating a population proportion P. And again, those binomial distribution, there's 4 things that you need to check. First one was that the trials were independent and they are performed a fixed number of time, that there's 2 mutually exclusive outcomes or disjoint outcomes, and then that the probability is the same for every single trial. Also, the higher level confidence leads to a wider interval and a larger margin of error. A margin of error, by definition, is the maximum likely amount of error between the sample proportion p hat and the population proportion p. It is also called the maximum error in the estimate and can be found by E equals Z alpha over 2, and again, Z alpha over 2 is found back on page 2. In our notes, that's the critical value. And then times the square root of p hat times 1 minus p hat, all divided by n. And then our error, E, is the upper bound minus the lower bound, all divided by 2. So a couple formulas that we do need to know. Some notes here. First one is that the confidence interval about the population proportion is of the form p hat plus or minus E. The point estimate, p hat, is the midpoint of the upper and lower bounds. And 3, the margin of error is the difference between the point estimate and the lower bound. So a few more formulas that we will add in here and some visual representation of what we're talking about here. So our point estimate is in the middle of our upper bound and our lower bound. And to get our upper bound and our lower bound over here, we're going to add our margin of error and subtract our margin of error from our point estimate. There are different ways to write your answer. As stated up above, you can write it as p hat plus or minus E, or we can also write it as an interval, which is going to be p hat minus E, comma p hat plus E, or the third way is as a trilinear inequality, which is going to be p hat minus E is less than P, which is less than p hat plus E. And the wording for the last one that we have is a trilinear inequality. We can also think of p hat, as stated up above, is the midpoint of the upper and lower bounds. And so in order to find that, we would take our upper bound and add our lower bound, and then divide by 2 in order to find that midpoint. The example below this says, express the confidence interval using the format p hat plus or minus E and round 3 decimal places. The confidence interval for the proportion of red M&Ms is 0.0434 is less than P, which is less than 0.217. So in order to find our p hat, we can take our upper and lower bounds and add them together. And so our upper bound is 0.217 and add our lower bound, which is 0.0434, and then divide the entire thing by 2. Doing that, we end up in rounding 3 decimal places is 0.130. E, which is our margin of error, as stated up above, is our upper bound minus our lower bound, all divided by 2. So upper is 0.217 minus lower 0.0434. And then again dividing by 2. And our margin of error, rounding 3 decimal places, is equal to 0.087. And it does ask for us to express our answer as p hat plus or minus e. And so our p hat is 0.130 plus or minus e, which is 0.087. Below this, we talk about how to use the graphing calculator in order to find our confidence intervals. So constructing a confidence interval for the population proportion with a TI-83 or 84 calculator, step 1 is going to be to compute p hat, which is x divided by n, which we did previously. Step 2 is verifying the requirements that we had stated up at the top of the page, which is that it's a simple random sample, the binomial distribution is satisfied, and that n times p and n times q are both greater than or equal to 5. From there, we're going to go to Stat button on our calculator, scroll over to Test, scroll down to 1 prop z int, and enter in x and n values, your confidence level or your C level. Highlight Calculate and select Enter. The answer given to you is written in interval notation. It's going to give you a lower limit and an upper limit. And then the last step that we do have is to interpret our results and talk about them. At the top of the next page, we have an example. And in this example, we're going to go ahead and circle this one, and we'll work on this one together in class. Right below this, it says, as sample size increases, the result is a narrower confidence interval, and a margin of error is going to decrease. We have the next box on here. It says the sample size needed for estimating the population proportion P. So again, this is estimating the population proportion P. We will have another set of formulas when we are estimating the population mean. So when the estimate p hat is known, to find our sample that we need, n, we are going to do z alpha over 2, which again is on page 2, which is our critical value, squared times p hat, and then times q hat, where q hat is equal to 1 minus p hat, all divided by e squared, and we do round up to the next integer. So no matter what, we are always rounding up. When no estimate p hat is known, n is equal to z alpha over 2 squared times 0.25 divided by e squared, and again we are going to round up to the next integer. There's an example right below that says find the sample size, so it does want us to find the sample size needed to estimate the percentage of California residents who are left-handed. Use a margin of error of 3 percentage points and use a confidence level of 99%. So part A says assume that nothing is known about the percentage of left-handed residents in California. And since we do not know anything about anything prior or p hat, no prior estimate p hat is known, then we have to use that second formula that we have listed, which is n is equal to, and it's z alpha over 2 squared times 0.25, all divided by e squared. So in order to get z alpha over 2, you need to go back to your table at the bottom of page 2. And at the bottom of page 2, you'll notice that when our confidence level is 99%, our critical value that we have is 2.576. We are going to square it times 0.25 divided by e, and e in this problem is our margin of error, and it says that it is 3 percentage points, and what that means is 3%. We need to express this as a decimal, so this is 0.03, so 0.03 squared. Plugging this in on your calculator, you get 1,843.27, and I also want you to note that we always round up, so it doesn't follow your normal rounding rules. So this is going to round to 1,844 people. So in order to conduct this research and find this confidence level, we need to sample 1,844 people. Part B says assume that based on the prior studies, about 10% of Californians are left-handed. So since we know that about 10% of Californians are left-handed, we do know p hat. So p hat is equal to 0.10, again 10%. And then q hat is going to be 1 minus 0.10, which is 0.90. So since we do know a prior estimate, we're going to use that first equation that we have listed, which is z alpha over 2 squared times p hat times q hat, all divided by e squared. So substituting in all the same values that we have from up above, except for putting in that p hat and that q hat instead of the 0.25. P hat again is 0.10, q hat again is 0.9, and e is 0.03 squared. Putting this all in on your calculator, I'm going to round 2 decimal places. I get 663.58, but again, we need to round up. And so when we round up, we get 664 people. So if you notice, since we had more information, we had information about a prior estimate, knowing that 10% of Californians are left-handed, we needed less people to sample. We only have 664 people that we needed to sample versus 1,844 people that we needed when nothing was known from any prior studies. So a big difference in the amount of people that you have to survey. So the next page that we have is 7.2, which is estimating a population mean. So it says, remember, x bar is the point estimate of mu. We can use a z statistic to determine the probability of getting a certain sample mean if the sample is sufficiently large. N is greater than or equal to 30. If the sample is small, then the distribution is not normally distributed, and a t statistic must be used instead of a z statistic. The t distribution has more spread than a z distribution. You can see that in the diagram below. You notice there's a z distribution, a standard normal distribution, a t distribution when n is close to 30, and then also the t distribution when n is smaller than 30. So the t distribution is typically used to study the mean of a population rather than study an individual within the population. In particular, it is used in many cases when you use data to estimate the population mean. For example, using a sample mean of 20 homes to estimate the average price of all new homes in California, or when you use data to test someone's claim about a population mean. For example, is it true that the mean price of all the new homes in California is $500,000? The connection between the normal distribution and the t distribution is that the t distribution is often used for analyzing the mean of a population if the population has a normal distribution or fairly close to it. The role is especially important if your data set is small or if you don't know the standard deviation of the population, which is often the case. So, very important when you don't know the standard deviation, which is often the case. So we have a student t distribution, which says, suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, the distribution of t equals, it's x bar minus mu divided by our standard deviation divided by the square root of n, follows the student's t distribution with n minus 1 degrees of freedom, where x bar is the sample mean and s is the standard deviation for the sample. And so we will not have to calculate this by hand. We are going to be using a graphing calculator in order to do that. But we do definitely need to know the properties of the t distribution. First, the t distribution is different for different degrees of freedom, stating the number of that we have in our sample, n. And again, degrees of freedom is just n minus 1. 2, the t distribution is centered at 0, and it's also symmetric to 0. 3, the area under the curve is also equal to 1, just like what we saw with the normal distribution. The area under the curve to the right of 0 is equal to the area to the left of 0, which is 0.5. As t increases and decreases without bounds, the graph approaches but never equals 0. And the area in the tails of the t distribution is a little bit greater than the area in the tails of a standard normal distribution. As the sample size n increases, the density curve of t gets closer to the standard normal density curve, and this is called the law of large numbers. Remember that z alpha is used to represent the z-score whose area under the normal curve and to the right of z alpha is alpha. Similarly, so this is extending to our t distribution, is used to represent t sub alpha is used to represent the t value whose area under the t distribution and to the right of t alpha is alpha. So again, you would have a value on here if you had your normal distribution or your t distribution, and you would have t alpha on here. That means that the area to the right is equal to alpha. In order to find the t value with a graphing calculator, this only works for a TI-84. If you have a TI-83, we can program it to do this. So definitely reach out to me or look on YouTube to find a way to program this. When we have class again, you are able to go to the TMark and they are able to install the program for you on your calculator also. So to find the t value with the TI-84 graphing calculator, we're going to go to second vars, go down to number 4, which is inverse t. And also a little note here is that inverse norm is what you would use if sigma is known. So if the population standard deviation, and remember this is the population standard deviation is known. And inverse t, you guys are going to go ahead and input in the area to the left and the degrees of freedom, and then close your parentheses. So the example right below says to determine the following in round 3 decimal places. First one is to find the t-value such that the area in the right tail is 0.2 with 19 degrees of freedom. So quickly sketching our t distribution, which again is like our normal distribution, just a little bit wider. You'll notice that the area in the right tail is really small. It is equal to 0.02. And I'm going to go ahead and call the value down here t. And so in order to find this value t, I need to use inverse t. And you'll notice that you have the area to the left. And so the area to the left here is 1 minus 0.02, which is equal to 0.98. Because again, that total area under the graph is equal to 1. Comma, our degrees of freedom, which is stated that it's 19. On your calculator, we're going to go to second vars, and we're going to go down to inverse t, INVT, select enter. The area to the left on this problem is 0.98, so 0.98. Your degrees of freedom in this problem are 19, so select 19. Go down to paste, select enter, and enter one more time. And you get your t value of 2.205. From the graphing calculator, we get 2.205. So another way to write this is this would be t sub 0.02. Again, that area to the right is equal to 2.205. The next example says find the t value such that the area in the right tail is 0.10. And we have 32 degrees of freedom. So again, sketching our curve, and this time its area in the right tail is equal to 0.10. So it's a little bit larger than what we had up above. So this is 0.10. And then the area to the left would be 0.90. Again, 1 minus 0.10 is 0.90. And then in order to find this, we're going to do inverse t of 0.90, comma, the degrees of freedom, which is 32. Selecting enter after you have all of this plugged in on your calculator, and you get a value of 1.309. Again, another way to write this is t sub 0.10 is equal to 1.309. Part C says find the t-value such that the area to the left of the t-value is 0.05 with 6 degrees of freedom. So this time again, sketching our t-curve or t-distribution. It says the area to the left of the t-value is 0.05 and 6 degrees of freedom. So area to the left of t is 0.05. So here's our t-value, 0.05, very small. That means that the area to the right would be 0.95. In order to find inverse t, we have the area to the left, comma degrees of freedom, which is 6. Rounding 3 decimal places, we get negative 1.943. And again, you can write this as t of area to the right was 0.95 is equal to negative 1.943. Part D says find the critical value that corresponds to the 95th confidence, assuming 16 degrees of freedom. And again, assuming that this is a t distribution. So we're going to go ahead and draw our t distribution. Again, remember with confidence intervals, we are going to be looking at the middle part. So this would be 0.95. I'm going to go ahead and call first one t1 and we'll call the second one t2. That means that this is going to be, each tail would be the 0.05 divided by 2, which is equal to 0.025 in each of these tails, like we saw before in previous chapters. From here, we are going to find t1, which is equal to inverse t. And for t1, the area to the left is equal to 0.025, comma 16. And then working this out, rounding 3 decimal places, we'll get our answer. T2 is going to be inverse t. And this time for T2, though, we have to look at the area to the left, which is going to be 0.95 plus 0.025, which is going to be 0.975, comma 16. So from our calculator, the first t-value we get is negative 2.120, and the second is going to be positive 2.120. And again, our t-distribution is symmetric, so it should make sense that these are going to be one positive and one negative with the same value. And again, it's symmetric with respect to 0. Right below this, we have constructing a confidence interval for a population mean with a TI-83 or 84 calculator. Step 1 is verifying it's a simple random sample, the population is normally distributed, or n is greater than 30. Step 2 is going to be going to stat, test, number 8, which is the t-interval, and then also note right here that if you know the population standard deviation, we will use z-interval. Otherwise, we do use t-interval. If the data is raw, then highlight data and put your data into L1 and set the list to L1 and the frequency to 1. If summary statistics are known, highlight stats and enter in the statistics. Enter the confidence level following the C level, and then highlight calculate and press enter. From here, again, you're going to get the lower limit and the upper limit, and we also still need to interpret our results. The summary statistics for our randomly selected weights of newborn girls are N is equal to 205 baby girls, X bar is equal to 30.4 hectograms, S is equal to 7.1 hectograms, and the confidence level is 95%. Round answers to 3 decimal places. Part A says to find either the critical value T alpha over 2, the critical value Z alpha over 2, and it's whichever is appropriate. So if you look at what is given to us, you will notice that sigma is unknown. And since sigma is unknown, this means that we are going to be using our T alpha over 2 statistic or critical value. And so our T alpha over 2 is going to involve us to find that T value by using inverse T is going to be the area to the left. And to get a better idea of what we have in this problem, I'm going to go ahead and sketch a curve. So our T distribution confidence level is at 95%. So again, that goes in the middle. And then in each of these ends, it's going to be 0.025. And our critical values are positive values. So I'm going to go ahead and look at the right side t value that we have. And to find this, the area to the left of our t is going to be 0. And it's adding together 0.95 and 0.025 and getting 0.975, comma, degrees of freedom. And again, degrees of freedom are n minus 1. So degrees of freedom would be 205 minus 1, which equals 204. From our calculator, we get 1.972. And again, this is our critical value that we would have. Part B says to construct a confidence interval estimate for the mean. So in order to do this, we need to use our t-interval. On our calculator, we are going to go to Stat, Test, go down to t-interval, select Enter, and on this problem, we are given our data values. So I'm going to make sure that I have my statistics entered in there. X bar is equal to 30.4. The standard deviation for our sample is equal to 7.1. N, our sample size, is 205. And our confidence level for this problem is 0.95. Select Calculate. And up at the top, you will see your interval, lower bound and upper bound. From the graphing calculator, we get 29.422, so our lower bound, and 31.378. And again, that is our upper bound, and these are measured in hectograms. And so we can say about 95% of these confidence intervals of these confidence intervals will contain the true population mean and again we're talking about mean weight of newborn girls and about 5% will not. The next example says travelers pay taxes for flying, car rental, and hotels. The following data represents the total travel tax for a 3-day business trip in 8 randomly selected cities. Round decimal answers 3 places. So if you notice, we are given a list of values here that are going to be our taxes that you pay when traveling. So it says determine the point estimate for the population mean travel tax. Point estimate is asking for a mean. This is the mean, and that would be X bar. In order to find that, we can add all of our values up and divide by however many values there are. We can also do this by doing L1 and putting in all of our values into that, and then doing 1 var stats. Going ahead and using 1 var stats, I get 83.349. Part B says to construct and interpret a 95% confidence interval and estimate the mean tax paid for a 3-day business trip. Since sigma is unknown, we cannot use a z interval. We need to use a t interval. And again, this time we are given data. On your calculator, you're going to go to Stat, to Enter on Edit, and enter in all your data values into L1. Once you have all those data values entered and double checked, you're going to go to Stat, scroll over to Test, and then down to T interval. Since we have a list of numbers, this time will be selecting data. Our data values are in L1, and our frequency needs to be set to 1. For this problem, we have a confidence level that is given as 95%, so 0.95, and then select calculate and hit enter. And at the top, you will see your lower bound and your upper bound for your confidence interval. From the calculator, we get a lower bound of 73.046 and an upper bound of 93.652. Another way to express this would be that our mean is going to be between $73 and about 5 cents and $93 and about 65 cents. So interpreting this, we would say about 95% of these confidence intervals will contain the true population mean, and we're talking about travel tax, and about 5% will not. Part C says, what would you recommend to a researcher who wants to increase the precision of the interval but does not have access to additional data? We could decrease the level of confidence. Right below this, we get the box of star. This is to determine the sample size N, and this is the required sample size to estimate the population mean. Mu is given by, and before we look at these, remember that we did have two other formulas in order to calculate the sample size needed, but that was to estimate the population proportion. This is to estimate the population mean. So using whatever formula it is depends on the problem being asked. So N is equal to Z alpha divided by 2, which again is found on page 2, that's your critical value, times sigma divided by E, and then that whole entire quantity squared. The error, E, is also found by doing upper bound minus lower bound and dividing by 2. And again, as we had before, N is going to be rounded up to the nearest whole number. What could be done to increase the precision? A couple things that we could do to increase the precision of our confidence interval. One is to increase the sample size, and two is to decrease the level of confidence. Example on the next page says a recent Gallup poll asked Americans to disclose the number of books that they read during the previous year. Initial surveys results indicated that sigma is equal to 16.6 books. So again, this time we know the value is sigma. It is also asking about the number of books that you read. So part A says how many subjects are needed to estimate the number of books Americans read the previous year within 4 books with 95% confidence. We are estimating the mean instead of a proportion because we're talking about number of books. And since the number of books we would have is a value that is not a proportion, this would be a whole number of value that you had read during the year. This is going to be estimating the mean. And it's asking for how many subjects, which means we are looking for N. So our formula on the bottom of the previous page is N is equal to, and it's Z alpha divided by 2 times sigma divided by E, all squared. And Z alpha over 2, since we are dealing with a 95% confidence level, is going to be 1.960 times sigma, which was given to us as 16.6. And then we're going to divide this by our error, which is stated up above, and error for this problem is within 4 books, so E would be equal to 4. Also note that it's not a percent like the last one. This is just a whole value that we would have. And then we have to square all of this. Plugging this into your calculator, you get 66.16, and again, we need to round up. Rounding up, we get 67, and so how many subjects are needed? So we have to survey 67 people. We are going to look at part B and C together in class, but you may go ahead and try those on your own if you would like to see if you can get the correct answers.